Good afternoon, everyone. I think it's my pleasure to have you all here. The Kent Distinguished Lecture are sponsored through the vision of Paul F. Kent Memorial Fund, which was established in 1977 to support education in transportation engineering. The Paul Fraser Kent Distinguished Lecture was initiated in 2007, honors outstanding leadership in the field of transportation engineering. Paul Kent was a 1920 graduate of the University of Illinois in the Civil Engineering Department. As a highway contractor and material supplier, he owned and operated two Champaign-based companies, which is General Paving and Builder Supply. Throughout his professional career, he expressed the highest regard and great esteem for the education in civil engineering, especially at the University of Illinois. He dedicated himself to civic service in Illinois and surrounding states. He was the founder and president of the University of Illinois Civil Engineering Alumni Association, which is now the largest in the country in civil engineering, and was the recipient of the University of Illinois Loyalty Award and the Civil Engineering Distinguished Alumnus Award. And today we are very, very pleased to have a very distinguished speaker with us and a good friend of many of ours here, Dr. Schwartz. Chuck Schwartz received his BS, Master's, and PhD from MIT, all in civil engineering. He is currently a professor in civil engineering as well as the chairman of the Department of Civil Engineering at University of Maryland at College Park, where he teaches courses related to pavements design, analysis, advanced soil mechanics, and computational geomechanics. His research interest and experience span the areas of analytical and numerical modeling techniques for pavement structures and characterization laboratory testing of pavement materials. He has played leadership roles in many national research projects sponsored by the government, federal government, state governments, as well as local government and the industry. He has been serving on several national boards for international journals in his field. He's very well known. I don't think that we need to give him more than that or talk more about this. I think we're very, very pleased to have him with us today as our Kent Distinguished Lecturer. Chuck?
Great. Thank you. I'm not sure I recognize the guy in that introduction there, but thank you. It's a pleasure to be here at the University of Illinois. I always enjoy my visits to campus here, and I'm pleased to see that things at Illinois are pretty much the same as they are at the University of Maryland, and that nobody sits in the front row. So today I'm going to talk about some work, several related projects that we've been working on over the past several years on structural characteristics and environmental benefits of cold recycled asphalt paving materials. And these are asphalt stabilized cold recycled materials. So I'm going to try to cover a lot of ground here. So I may skip over some of the slides pretty quickly. First, I want to talk about the structural characteristics of asphalt stabilized cold recycled pavement materials, because this is largely unknown, especially in the context of modern mechanistic empirical pavement design. We just don't really know what the properties of these are. And so we started with an initial case study that we did for the Maryland State Highway Administration on one class of materials, and then have been generalizing that through a national study under the National Cooperative Highway Research Program. I'll talk about both of those. And then more recently, we've been working on investigating the environmental benefits of these, and in particular the greenhouse gas savings that accompany recycling, and in particular in-place recycling. And this work is actually funded by local industry, global resource recyclers, who their end objective here is to try to be able to generate revenue streams from trading of carbon tax credits from the emissions savings. So for the first project, we were focused on foam stabilized materials, which are an interesting class of materials that are somewhere in between asphalt and unbound materials. It's a cold process. The aggregates are cold and they're wet. And what we do is we take hot bitumen and inject water into it. It creates a foam, and we spray it on the aggregates. And what it does is it coats the fine aggregates, and then the asphalt coated fine aggregates under compaction bond together the larger aggregate particles in the mixture. And the aggregates can be anything. Very commonly they're recycled asphalt pavements, but they can be recycled concrete, they can be virgin aggregates. But so generally we're looking at adding about 2% binder in these foam stabilized materials. And this can be done two ways. It can be done using a cold central plant recycling system as shown in the lower left. And these central plants actually are mobile. You can take them to the job site or you can keep them parked at your production facility. And we're also looking at cold in-place recycling or full depth reclamation. And again, the applications are, if we're looking at CIR and CCPR, we're really looking at milling off just part of the asphalt layer, recycling it, putting it back down, and then putting a hot mix surface course on top of it. For full depth reclamation, we're going deeper into the granular base and even in some cases to the subgrade. But again, stabilizing it, putting it back down, compacting it, and then putting a surface layer of HMA on top of it. The mix design for these materials is fairly crude, and in fact some agencies don't even go through a formal mix design process for these materials. But the most commonly accepted mix design process is in terms of indirect tensile strength. So you make essentially Marshall-sized pucks and you do an indirect tension strength test on it, and there's usually a specification for a minimum wet tensile strength and a maximum tensile strength ratio. There's also some requirements on the foaming characteristics of the binder that you need to satisfy. But basically the key thing here is that the mix design is based on strength, which again for pavement design is not really the thing we're interested in. Okay, for a well-designed pavement we should not be near the failure limit of these materials. We're interested in stiffness, not strength so much. So we had the opportunity to test these materials on a lane addition project on Maryland 295 just outside of Baltimore Washington International Airport. So it's it's a high volume road, not a lot of truck traffic, but some. And we had, without going into the details, we had three different segments of foam stabilized base material and a couple of graded aggregate base sections that we could use for controls. And then there was a control strip that was paved early in the project to get compaction patterns down. And this particular mixture that we were looking at here was a little bit unusual in that more commonly these foam stabilized materials or foamed asphalt stabilized materials would be 100% wrap. In this particular case, this supplier used 60% recycled concrete and 40% wrap and a 2.8% foamed asphalt. And you can see a little bit of the details here on the gradation characteristics and some of the mixture design characteristics. And again, on that last line, if you look, the foam stabilized material is being placed at a fairly high moisture content because it's compacted, essentially using Proctor compaction theory. You run Proctor compaction tests on this material, figure out the optimum moisture content, and compact it at that level. So on this particular test, we were interested in doing field stiffness evaluations of this material. And so on this, again, there was a control strip and two production segments that were placed in the summer of 2011. And we had several things that we were testing here. We did standard nuclear density gauge testing, which is a little bit tricky on these materials because of the bitumen content, the water content reading from the nuclear gauge is thrown off, and so you've got to do a correction for that. We had a geogauge for measuring stiffness. We had actually several LWDs, but the one we use the most is the Zorn LWD, lightweight deflectometer. And then also we had the State Highway Administration come in and do some conventional FWD testing. So one of the things we were interested in was to see so how the properties of these materials change with time. There's a curing process that goes on in the field with these stabilized materials. You put them down and they get progressively stiffer over time, and we wanted to track that in this case study. And that's exactly what we measured. If we go in, and again, those of you who have worked with these in situ stiffness devices know that they all give different values and they don't always agree with each other, and we found that here that the stiffness we got out of the Zorn LWD was different than what we got out of the GeoGauge, and was different still from the Dynatest LWD. But you can see the trends here. The red lines are the foam stabilized base, and so we get about roughly, what is that, about a tripling of the stiffness in the first week of curing. And again, this is uncovered at this point. We've placed this material, compacted it, and it's just there in the sun. We also had a stiffening of the granular base. Okay, and you can see that as the light blue curves, and that roughly doubled in stiffness. And that's simply due to drying. Okay, if you look at it this from a partially saturated soil mechanics perspective, now if I'm placing this material at 8% moisture content, whatever, it's July in Maryland, it dries out, and so I develop matrix suctions, and so that's an increase in the effective confining stress, and we see an increase in stiffness just because of that. And so some of the increase we see in the foam stabilized base material is also due to drying, and so one of the things we wanted to try to do was to separate out those two effects. And so we did this in a fairly straightforward way. We took the empirical unsaturated soil mechanics models from the MEPDG and used that to try to estimate what increase in stiffness we could expect to see as a consequence of changes in saturation level. That's all. And it actually turned out to work. And there were actually two versions of this. There's the upper equation is the one that's in the MEPDG model, and then Claudia Zapata and her students at Arizona State had come up with an enhanced model that included some density effects and other things. And so we looked at both of those. And okay, so this is the similar to what I had before. So this is increase in stiffness is measured by the LWD. So you can see the raw data over on the left. And then on the right is plotted essentially the ratio, is this F sub U, it's the ratio of the moisture adjusted modulus to the modulus under optimum moisture conditions. And so you can see that the material was placed at optimum moisture and density, and the foam stabilized base increased by about a factor of 3. You can see how much the granular material increased, and those bars over on the far right are telling us how much what the increase in stiffness would be just due to the drying effects. And you can see that the granular base actually agrees quite nicely with this, that the increase in stiffness that I'm seeing there agrees pretty nicely with what the empirical unsaturated soil mechanics model would predict due to drying at that point. Now, it also looks like the foam stabilized base material is influenced, or is also mostly drying if you look at this. But there's another effect that's going on here that we had to correct for, which is that we're testing on a granular base layer that's only about 8 inches thick, and the zone of influence for the LWD goes below that. Okay, and so the readings that we're getting from the LWD are a combination of the stiffness of the granular base and the subgrade stiffness. Now, that has more of an effect for the foam stabilized base material because that is a stiffer material, and the softer subgrade underneath has more of an influence. The granular base had a stiffness closer to the subgrade, getting closer to homogeneous conditions. And so when you go in and correct for the finite layer thickness, you can see that, I don't have a good pointer here, but so we've got, no, this isn't going to work. Nope, can't get the mouse over there. All right, well, I'll have to, oh, there it is. Okay, so these were the measured values, and this is after making the adjustment for the influence of the soft subgrade underneath. And again, the effect was most pronounced for the granular base layer, for the foam stabilized base layer, and not so much for the granular base layer. And so when you make that correction and go over here and look at this curve, now we can see that in fact there is a lot more going on than just drying in the foam stabilized base material. That after I make that adjustment for the finite layer thickness, I'm getting about an 8-fold increase in stiffness in that first week for the material in that layer. Oh, great, thank you. Oh, excellent. I can move. Okay. No, if you want to move it, then we'll put this in. Okay. Yeah, but then I got to put on the lavalier mic, so I'll just stay put. Thanks. Okay. Now, so this is just 7 weeks, 7 days rather, after placement. And then we pull off the job and stop taking readings. Now, just before opening for traffic, it opened for traffic about 6 months after placement. We went back and did FWD drops on the material and saw what had happened. And oh, I still need to put this in. Yeah, I need to put this in. Oh, just August. So we came back and did the back calculation analysis, and some interesting results. Okay, so we get sort of reasonable modulus values for the surface layer, A little bit lower on top of the GAB because that was a little bit stiffer than these other sections which had the stiffer. This is a little softer than the other sections which had the stiffer base layer, and so I'm compacting against a softer layer. I'm not getting the same amount of compaction as I am on the other sections. You can see the subgrades coming in pretty uniformly all along. And the thing here that we're interested in is the base layer. Okay, and there's a fair amount of variability, but you can see that what's happened here is we've got an enormous increase in stiffness now 6 months out. If I back up, okay, so after 7 days we were up at what, about 450 megapascals for stiffness, and now oh great, different units. But this is about a sevenfold higher stiffness at 6 months than it was at 7 days. So something really has been going on here. If I look at the 7-day stiffness, the cold central plant recycled material after 7 days, the stiffnesses were all down in that region. So in that intervening 6 months, 4 to 6 months, depending on which section I'm looking at, we had an enormous gain in stiffness due to field curing of this material. And again, this was not terribly surprising to us because others had found this in the literature. Andreas Loisos in Greece had looked at a foam stabilized project and did falling weight drops over time after construction. And there's a lot of scatter here. I tried to fit in the mean trend here with the red. And you can see also that a big increase in stiffness, most of it taking place in about the first 6 months after placement. Okay, so our results sort of match that. And but the clear thing here is that if we want to get a good estimate of the structural characteristics of these materials, we really have to do it in the field cured condition. That immediately after placement is no good. Doing it on laboratory prepared specimens doesn't work because it's virtually impossible to reproduce this field curing phenomenon in the laboratory. So we really have to go in and try to do it from field cured samples, which is what we did. We decided to go in and do some structural property testing. So we ran some tests through our UTM 100, and at State Highways run some through their AMPT device. And the properties of interest here are the ones that we're interested in primarily for mechanistic empirical pavement design. So we're interested in stiffness, which means dynamic modulus. And again, here we're going to be looking at axial for the moment. But in the general case, if I'm looking at in-place recycled materials, we've got some considerations here about specimen size. That generally, if I'm doing cold in-place recycling, I don't have a tall enough specimen to do an axial specimen, and I might have to do IDT, dynamic modulus. But we're interested in getting the master curve and the temperature shift relationships for these materials, and we're interested in permanent deformation characteristics. Right? What are the slope and the intercept of the secondary stage, so I can predict rutting in these materials. I'm sort of skipping over some of the details here, but there was some debate going on about, so what's the best way to characterize these materials? Do you characterize them as unbound materials, or do you characterize them as asphalt materials? And our judgment in the end was that the temperature effects and the loading rate effects were sufficiently strong in these materials that they really should be treated like asphaltic materials. Maryland has not transitioned completely to the MEPDG. Very few states have transitioned completely, so they were also interested in what the properties were for the 93 AASHTO empirical design method. So that means trying to back out a layer coefficient for these materials, which is going to be a function of the stiffness. And so we tried to do that also. But again, so what we did is we went in, just before opening for traffic and took cores roughly 6 months after construction. Took them back to the laboratory. I should mention here that the pavement section on this was 8 inches of foam stabilized base material placed in 2 lifts. Well, it wasn't consistently 2 lifts, but 8 inches of foam stabilized base material, and then on top of that, 8 inches of hot mix. And I think part of what's going on in the field curing is that when you put that hot mix on top of it, a lot of the heat flows out through the bottom of the mat, and that's flowing into the stabilized material. And I think that's doing the final cooking of this stuff that really solidifies the bonds. But the point is, when we tried to core this a couple of weeks, a month after construction, you couldn't get cores out. The foam material would just crumble. When we went in at 6 months and took a core out, we got this 16-inch long core that if I didn't know that it was foam stabilized material on the bottom, I would have said, somebody put down 16 inches of hot mix. It looked that good at that point. And so we went and we ran, dynamic modulus, and it's a recycled material. There's a fair amount of variability, I'm trying to give a little bit of an indication here up on the top of some of the variability. One of the things we were interested in is, so how did the stiffness of these recycled materials compare with hot mix asphalt? And that's shown on the lower left, where the black dashed line is sort of we took a typical mix and plotted the master curve for it. And you can see that, in the middle to, middle to upper shelf regions of the master curve, that the cold recycled material is coming in at about half the stiffness of hot mix asphalt. We also looked at, there we go. We also looked at repeated load permanent deformation behavior. And again, a fair amount of scatter, but one of our interests here was to look at how this compared with the same behavior for hot mix asphalt. And so the solid lines, the solid and the dashed lines all correspond to the foam stabilized material. The two curves at the top that go into tertiary flow are from some laboratory prepared specimens that just failed prematurely. And again, that's in part because it's so difficult to replicate the field curing conditions under laboratory curing. The dotted lines are what we had for, again, some typical hot mix mixtures that we had tested in the past. And the takeaway from this is that in broad terms, the repeated load permanent deformation behavior of this foam stabilized material was comparable to what you'd have for hot mix. Okay. And that's okay, because these materials are generally going to be lower in the pavement structure. They're not going to be right at the surface. Most of the rutting in the asphalt layers are going to occur in the upper few inches of the pavement section. And so we've got reasonably decent repeated load permanent deformation characteristics here for a material that's going to be deeper in the pavement section. Rutting should not be a problem. Okay, and then to make our sponsor happy, we tried to back out what a layer coefficient was. And again, here's another philosophical discussion. Okay, when we talk about layer coefficients, is this an A1 or an A2? Is this an asphalt layer or is it a base layer? We went back and forth on that. If you go into Vertgen's chart from their design manual with the mixture properties we had, you would back out something of a layer coefficient of about 0.28. We went a little bit farther. Since we had stiffness measurements both from laboratory assessment and from FWD drops, we tried to plot those up, and we looked at all of the various relationships that are available in the 93 AASHTO guide for getting at layer coefficients. We looked at it as an asphalt material. We looked at it as an unbound material. We looked at it as an asphalt stabilized material. We sort of looked at all of those relationships and plotted them all up, and then sort of eyeballed it and made a judgment. And so on this graph here, you can see the scatter in the data. In the boxes show sort of the mean and standard deviation ranges for all of that data. And so, we sort of hung that on the wall for a while and stared at it, and then at the end of the day said, well, okay, I think that maybe values like this are about right. So in terms of layer coefficients, if I've got something that just meets the spec of a indirect tension strength of 40 psi, which is over on the right, then we got a layer coefficient of something on the order of 0.3 to 0.32. We also looked at 100% wrap material, or tried to estimate for 100% wrap material. If I've got something that exceeds the specs a little bit and I've got a 50 psi wet indirect tension strength, then we're somewhere up at 0.35, 0.36. And again, if you look at like a base asphalt mixture, what would you use? What does Illinois use as a layer coefficient for a base asphalt mixture? 0.4, something like that. So, this is sort of like a low quality asphalt base mixture is what our judgment was at the end. And so in the end, we came up with some recommendations to the State Highway Administration that for specifications that, they should base it on a minimum of 45 psi soaked ITS and TSR, maximum TSR of 70%. And that corresponded to a resilient modulus of around 350 KSI and a layer coefficient of about 0.32. And they were happy with that, and been designing sections using that now. But this was sort of an introduction, to me at any rate, in these materials. And as it so happened, at the same time, I was talking with and working with Brian Diefendorfer from the Virginia DOT, who is in the midst of doing a big reconstruction project on I-81, which is one of the major truck routes through the Shenandoah Valley. And they were doing a combination of cold central plant recycling, cold in-place recycling, and full depth reclamation. And he was finding exactly the same things, that when they went in, they could measure an initial stiffness increase. When they went in 4 to 6 months later and did FWD drops, they saw a whopping increase in the stiffness. So it's consistent trends, and they seem to be real, because the section that they rehabbed of I-81 was something that it's a terrible subgrade. They would have to go in every 2 or 3 years and do major maintenance and rehabilitation to it. This thing has now been in service for about 4 or 5 years and looks very good. So the material has been holding up. So, but as a consequence of that, Brian and I teamed together to pursue the NCHRP 951 project, which was intended to determine the structural properties of these materials for use in mechanistic empirical pavement design. So we're looking at again, asphalt stabilized, cold in place recycling, and full depth reclamation. And so our focus here was on the in situ structural properties, again, under field cured conditions, because these are going to be the relevant ones for the pavement service life, and to develop the material property inputs that we need for the pavement ME design program. So that means dynamic modulus and repeated load permanent deformation characteristics. And again, the repeated load permanent deformation characteristics go into the distress models for predicting rutting. And so again, many of you have seen the pavement ME design software, but basically we're looking for the numbers that go into these input screens in the software. And so the basic premise that we proposed, and the panel seemed to go for it, was that it only made sense to measure these things on field cured conditions. So we were going to have to go out and get cores at least 6 months after construction and measure the properties on those. And then our hope was that those after the fact field cured structural properties could be correlated back to mixed design properties and field conditions during placement, so that in the design stage we could have some sort of predictive model that would tell us what kind of properties we'd have in the field cured condition. And this was kind of an unusual team, I think, for NCHRP projects. Many of my faculty colleagues here have pursued and successfully and sometimes unsuccessfully NCHRP projects, and forming the right team is often one of the biggest challenges and the biggest opportunities. And this one was unusual because so here I was at the University of Maryland, a conventional university-based researcher. Then we had Brian Diefendorfer at the Virginia Center for Transportation Innovation and Research. So it's an agency. It's an operating. This is the research arm of the Virginia DOT. And then we had 2 industrial partners, Wirtgen America and Colas Solutions, and their role was to help us identify projects. Since they were providing the technical support to agencies that were actually building these projects, they could identify suitable projects so we could go to the agent, and they could provide the entree to the agencies so we could try to persuade the agencies to go back the following construction season and core these roads for us for testing. And we're still in the middle of this. Okay, so this is a work in progress, but we've got some results that are at least worth looking at right now. We're actually in the analysis stage right now, where we finished all the field sampling and the laboratory testing. And in the end, we got 25 projects in 13 different locations, a little bit fewer than we had expected, but the severe winter in not 2014, 2015, but 2013, 2014 depleted agency budgets because they had extra snow removal costs, and the construction season started very late that year, and so they weren't able to provide us with as many projects as we had hoped on that second season of the project.
Chuck,
yeah.
What's the Illinois project? No problem.
Yeah, I'd have to go back and check the data. It may be around this area, if I remember correctly. Stephanie Drain, I think, helped us get samples for that. Now, one of the problems we knew we were going to encounter here, particularly for CIR, is that the lift thicknesses are just not great enough to do conventional laboratory testing. we're looking at most 6 inches for a CIR layer and typically less than that. And so the question was, how are we going to measure dynamic modulus and repeated load permanent deformation characteristics for these thin lifts? And originally we thought, well, we could do it using indirect tension testing. Richard Kim at North Carolina State has worked out a way of doing that. We tried it, didn't seem to work very well for these materials, and so we decided to go a different way. And we decided to capitalize on some work that Nelson Gibson at Federal Highways had started on looking at substandard size cylinders and doing testing on those. And so we thought, well, this is worth pursuing. And what we would do in that case is we would core horizontally, okay, because we could get a 2-inch diameter specimen if we cored. These are 6-inch cores, so I could get a 2-inch diameter by roughly 6-inch long cylinder out of it if I cored horizontally. And we wanted to see if we measured those kinds of specimens, if we would get the same results as we would with full-size specimens. Now, since we had a limited supply of the recycled material, we did our preliminary study on hot mix asphalt, and we looked at a couple of diameters and a couple of heights and a bunch of mixtures. Brian kind of went a little over the top on this, but we got a good set of data, and we were comparing small scale versus full size. And this just shows the setup, a special coring jig where you could go sideways through the cores. And you can see it over there, the cored specimens on the bottom left. And then on the AMPT jig for attaching the instrumentation points, Brian had to do a little bit of machining to adjust the arms so that they would reach in on these smaller diameter specimens, but that was a fairly straightforward operation. And so at the end of the day, when you plot up the data, it looks pretty good. Okay, so you've got the small scale specimen, dynamic modulus values along the vertical axis, the full-size, conventional cylinders along the horizontal axis, and yeah, there's some scatter, but I'd say that certainly, my view is that, yeah, there may be some errors in this, but since we don't have a clue as to what the dynamic modulus properties are for these cold recycled materials, I'm willing to tolerate, a 10% error. That's okay. So we said this is good enough. We're going to go this way. And so then we started coring the recycled materials and doing the testing. And if you plot up all the master curves, they look sort of like this. And not a whole lot of pattern that we've been able to distinguish out of this so far. Now, this is not the most useful way of comparing all of these data. And so what we did is we said, well, let's identify some key dynamic modulus values out of the temperature and moisture combinations or frequency combinations that we looked at. Let's choose something. Let's choose the one that's closest to the upper shelf, one that's closest to the lower shelf, and one sort of in the middle, and use those as fingerprints for the dynamic modulus master curve. And so we plotted those up, and here you can see things now segregated out by the mixture type. So we had FDR emulsions. Okay, so I skipped over that, but the first project I talked about was just foam stabilized materials. The NCHRP 951 included both emulsion and foam stabilized materials. So we had some FDR emulsion projects, foam projects, cold in place recycling emulsion and foam, and we had some cold central plant recycling emulsion and foam projects. And here you can see the 3 different dynamic modulus fingerprint points on here. And the interesting thing here is that if you look at this, there's surprisingly little difference among these different types of materials. About the only consistent trend that you can see here is that the cold central plant projects on the far right tend to come in a little bit stiffer than the in-place recycling projects. And that sort of makes sense. You've got more quality control over the cold central plant recycling. Some of the producers actually try to fractionate, try to sieve their aggregates a little, their wrap a little bit before making it. So I've got better quality control, and so that shows up here as better stiffness. The real key here, though, again, is, so all right, that's fine, but how does this compare with conventional hot mix mixes? And so here we've got some typical HMA values, and these, unfortunately, I didn't have a lot of data for base mixtures, which would be the better comparison because we're using these really toward the base of the asphalt layer. I mostly had data for surface mixtures, which are going to be stiffer. But if I go in here at 40 degrees, I'm sorry, this is, the 40 degrees C, 1 hertz, the lower shelf value, the middle point. Yeah, right, okay. So here are the sort of ranges of the hot mix asphalt dynamic modulus values at those same temperature and loading rate combinations. And again, there's some scatter. We had something on the order of 20 mixtures we looked at. So you've got a range of values here. And if you look at this, look at this long enough, you come away with the conclusion that, as we saw in the first project, that roughly these recycled materials, these cold recycled materials are coming in with stiffnesses roughly half of what we have for hot mix asphalt. Okay, so is that good or is that bad? Well, that's one of the things we're in the process of analyzing now in the analysis stage. One question would be, so what's the impact of that going to be on performance of the pavement as predicted by the MEPDG? And that's what we're looking at. But roughly, again, the takeaway is that these materials, not a lot of variation among the different types of materials, and coming in at roughly half of hot mix asphalt. Here are the repeated load permanent deformation curves. And I've forgotten what the story is with that orange one, but something screwy went on in the test in that. And again, these are all measured from field cured cores, the small cylinders also. And so we went in, again, with some key repeated load permanent deformation parameters to try to sort this out a little bit. So we looked at the slope and the intercept of the secondary stage. And we also looked at the accumulated plastic strains at 1,000 cycles, which is roughly the beginning of the secondary stage, and at 10,000 cycles at the end of the test. And here's how the data shake out. And again, the CIR projects tended to show a little bit higher did show a higher susceptibility to rutting. If you look at the microstrains at 1,000 cycles and 10,000 cycles, the cold central plant materials and the FDR materials all came in sort of roughly at the same values. And again, if I try to superimpose typical HMA values for surface mixes, I get things that sort of look like this. And I can see that, well, okay, for the FDR and for the CCPR materials, it looks like we're sort of in the same ballpark as we have for hot mix asphalt. Our CIR is a little bit more problematic, but again, these materials are going to be deeper in the pavement structure. And so even though they're more rut susceptible, it's not at all clear that that's going to translate to increased, significant increased surface rutting. Now, okay, so where we're at right now is trying to develop these correlations, and frankly, it's not been easy going right now because, as you've seen, there's not been a lot to distinguish the properties of these different kinds of materials. I mean, there's quite a bit of a difference between, an emulsion FDR project and a foam cold central plant recycled project or mixture. But we're attempting to do the correlations, and again, trying to relate the mix design, the things we know in advance, the mix design properties. What were the conditions during field placement? Was there field QA done? Was density taken? What are those properties? And we're hoping to correlate those with the actual structural properties that we're interested in, the dynamic modulus and the repeated load permanent deformation, and again, measured from the field cured cores, the sort of after the fact structural properties, and then looking at that in terms of performance modeling and predictions. And so, the correlation analysis, just to give you a flavor for it, so for the inputs, we've got a lot of things. We've got gradation, we've got, how much stabilizer we've got. In a lot of these mixtures, we will throw in a little bit of Portland cement as an additive. If it's a foam project, what were the tensile strength values? If it was an emulsion, what's the stability values? And then, construction, what was the recycling depth, bulk density after compaction, curing time, how long has it been sitting there, what was the overlay thickness? And then the outputs we're looking at, well, we're sort of fishing right now. We're looking at, at dynamic modulus at these key sort of fingerprint points, different temperatures and loading rates. We're also correlating things with the master curve parameters. And for repeated load permanent deformation behavior, again, the plastic strain at 1,000 or 10,000 cycles, but more importantly, the secondary permanent deformation parameters, the slope and the intercept. Flow number, not so much. None of these materials really went into flow for the conditions we tested. And we tested using the NCHRP 930A recommendations for hot mix asphalt. And again, flow number is really just a screening parameter anyway. It doesn't tell us a whole lot about predicted performance. And then, we want to use the results from the correlation analysis then to actually develop a model that will allow us to predict what the structural properties are based on these input values and sort of leaning toward these artificial neural networks, which we've applied we and others have applied very successfully to a whole lot of these kinds of predictive models. But that's where we're at right now. We're trying to sort all of that out. But as things stand right now, again, we were able to successfully measure these structural properties from these small cylinder specimens, which again, if you're looking at overlays, even for hot mix overlays, this suggests this is the way to go to get those structural properties. We went and actually measured the properties from these 25 mixtures at 13 locations. And as I said, the modulus values are about 50% of those hot mix asphalt, a little bit lower for CIR, and the repeated load deformation behavior is similar to HMA, except again for the cold in place recycling, which tends to be a little bit more rut susceptible. So the CIR is sort of the outlier. It's a little bit less stiff and a little bit more rut susceptible than the other classes of material. And again, what we're doing right now is the correlation analyses and the neural network modeling, and then the last analysis work is looking at sensitivity studies to see, okay, if I use these cold in-place recycling or cold recycled materials in place of other rehabilitation strategies, what's the impact on performance, which is really the thing we're interested in at the end of the day. Okay, take a deep breath, shift gears. That was all on structural properties. Now, the thing we've been working on more recently is looking at the greenhouse gas emissions. And this is a project that, again, is being funded by one of our local producers. I was sort of involved in helping get the project going and connecting up the right players. And we've got somebody on the faculty who is actually much better than I am on the sustainability stuff, who has taken the ball and run with it. But what we've been doing is a complete cradle to placement greenhouse gas analysis for these processes. We're looking at conventional hot mix asphalt pavements, cold central plant recycling, and cold in place recycling. And again, it includes everything. It includes the embodied carbon in the raw materials going into the mixture. It's including all of the emissions from the production process for the materials. It's including the emissions from all the transport of materials, both into the plant and then transporting the produced materials out. It includes all the emissions from the construction processes in placing this material. And this just shows the sort of the major steps in it. We've got so here's all the raw materials going in, so it's all the embodied carbon in those, and then we've got the production process here, including everything, even the emissions from heating the plant office goes into this, and then the transport to the job site, and then the whole laydown process and all the emissions for that. And so that last picture would apply to both hot mix asphalt and for cold central plant recycling. For the cold in place recycling production and placement, basically the raw materials are on the ground, most of them. I mean, we bring in bitumen and we may bring in the dry additive and water, but there's much less import of new materials and there's much less transport, since we're essentially milling up the material, stabilizing it, putting it right back down there, so we don't have a lot of trucks running back and forth, and that's a big savings in emissions. And so this is the thing that's a little bit different with the cold in place recycling process. And one of the things we wanted to look at is that not just the emissions embodied in the materials, not the emissions per ton of material as would be suggested by those last flow charts, but also recognizing that the recycled materials aren't quite the same as hot mix in terms of structural performance, and so we have to make an adjustment for that. If I'm going to use 4 inches of hot mix asphalt, I might have to use 6 inches of CIR to get the same structural capacity. And so we needed to do an apples-to-apples comparison. We wanted to design pavement sections for each of these conditions that had the same performance. And so we had a baseline scenario, which is the hot mix asphalt. So we had designed a section for that, and then we looked at the foam stabilized base, or a foam stabilized bitumen pavement. So we're looking here at either cold central plant recycling or cold in place recycling. My colleagues who did this also threw in a Portland cement concrete pavement section, and but the data we have on the emissions for that isn't quite the same as what we have for the asphalt materials. I'll throw it in, but I'm going to focus on the asphalt system. Now, you need a lot of data to do these emissions analyses, and a lot of it is available in standard databases scattered all around the literature. And we dug up all of this stuff, and there's databases for the embodied carbon emissions in the materials and for transport and all sorts of processes like that. You can get information on emissions for equipment usage for different categories of emission. The coal central plant is run by electricity, so there's emissions associated with that. And so there's a bunch of standard databases that we looked at to get at these and methodologies that are out there to do it. And in the end, what we're looking at are all these different emissions categories that we're all going to add up at the end of the day. Now, to supplement that, we also sent teams around to various sites around mostly the East Coast, some in California, to actually collect real project data. They would go out and they would log everything that was going on at the site, what equipment was being used, for how long, and so on, and brought it all back and did the actual emissions calculations for those specific projects rather than just using the generic database information. And and there's a fair amount of variation, but this is showing some of the computed emissions. So that we looked at for HMA, we looked at 10 projects, 16 producers, so that's the upper left, and then sort of in the middle is CIR. We had 5 projects, and for the CCPR, we just had 1 producer, the funder of the research, but 13 projects for that. And so we collected all that information, and again, this is information for real projects, the real equipment usage, the real material usage that went into it. Again, we also pulled out, I see what's happening here. It's none of these Mac to Windows things here. That's where the fonts are screwed up. We also got sort of standard information for, PCC pavements, and again, we'll include it here for a comparison. But the real thing here, so now just looking at the production and placement of the material, not making the adjustment for the fact that these materials have different structural capacities, you can see how this shakes out. So the hot mix asphalt came out with about 250 kilograms of CO2 equivalent per metric ton of material. CCPR comes in at about half of that. It's 75. Cold in place recycling, at roughly what is that? That's 20% of the hot mix asphalt. And the PCC comes out with the highest emissions, but again, the calculations on that one are a little bit shakier. And again, it's mostly from the production of the cement that goes into it. So then we went and we looked at a case study. Okay, we want to say, okay, now if you were going to use these products in a real pavement and now had to account for the fact that they have different structural capacities, how would things shake out? And so we took the Intercounty Connector, which was a major recent construction project in Maryland. We took a 7.2 mile length of it. It was completed in the late 2000s. And the original design, which is a straight HMA flexible pavement, conventional flexible pavement, was 2 4-inch lifts of 19 millimeter super paved mix with a surface course of 2 inches of 9.5 millimeter, and all of that over a 12-inch CR6 stone base. So that was our baseline pavement design, and then we designed. So we analyzed that using the mechanistic empirical pavement design guide and found out what the predicted performance was. And then we went in with a cold central plant recycled rehabilitation scenario and designed the pavement section so it would have the same predicted distresses at the end of its design life. We did the same thing for a CIR section. So now we're actually comparing things in a fair way that we've adjusted for the differences in structural capacity. And so when you go in there and look at this, the units are a little different here. Now we're doing it per lane mile. So again, the HMA, and here you can see it's broken out by, what are the emissions associated with the surface mix, the base asphalt mix, and the granular granular aggregate base. So our HMA comes in at about 550 metric tons of CO2 equivalent per mile. The CCPR material comes in at about 400, so roughly about 25% lower than the HMA. And the CIR comes in at roughly about half the emissions of the HMA. And again, just for comparison, there's the Portland cement concrete over on the far right. This, this is fairly significant. This is I can see a time in the not too distant future when states and agencies are going to start mandating stricter sustainability requirements that could include limits on greenhouse gas emissions for projects. And this kind of information is going to feed right into those kinds of scenarios. So anyway, to conclude, so again, looking at the structural characteristics of these cold recycled materials, again, in broad terms, a little bit, less than, or sort of less than a base asphalt mixture, or call it a low quality base HMA mixture. Again, a structural layer coefficient of around, 0.32 seems to be a reasonable number. Stiffness about half that of HMA. Repeated low permanent deformation behavior comparable to HMA surface mixes. And again, the CCPR seems to be slightly better than CIR and FDR. And again, I think it's because of the better quality control we have in the central plant produced material. And we really didn't see much systematic difference between emulsion and foam in any of these. Okay, and so, and the way this is evolved is some states do all emulsion stabilized materials and some do all foam. And, I think it's largely, depends on who got there first. Did Wirtgen get there first, or Colas, or, whatever. And then it becomes kind of a religion that, well, we've always done foam, we've always done emulsion. But from our results, we just don't really see much difference in terms of the structural performance of these materials. Again, I think a key finding was that, and again, Nelson Gibson had done some of the preliminary work on this, but we really, banged on this one pretty hard, and came away, with the conclusion that these small-scale specimens actually do a pretty good job of giving us good test results, good estimates of the structural properties. And then again, the final bit of this is the greenhouse gas emissions, substantially lower than for HMA and PCC. And as we saw just on the last slide, for the cold central plant recycling, for the case study we looked at, it was about a 26% savings. For the CIR, 53% savings versus HMA. And again, that's including the differences in the structural characteristics of these materials, as well as the differences in the production and placement processes. And right now, we're about halfway through this very laborious process to get formal certification of these greenhouse gas emissions savings. There are several NGOs that do this. The one we're dealing with is one called the Verified Carbon Standard. And again, it's this multi-cycle review process that is about halfway there. But again, the idea is that even now and certainly in the future, there will be a trading market for these carbon credits. And so these are a potential revenue stream for producers. And with that, I can open it up for questions.
Questions from Professor Schwartz?
Sure.
Yeah.
What was the standard failure criteria for the stabilized basis when you did the NDPDG comparisons? Were you dealing out with fatigue, rutting?
It was, I don't know, there's 85% confidence on this answer. I think it was rutting was the controlling distress.
You use the Bobby Lips thing?
That's the one that's in there, so that's the one we're using, yeah.
Okay.
But again, we're using the same one for all of the scenarios. So if it's wrong, hopefully the same way for all of them.
Just to follow up on that question, how were the thicknesses different then when you switched from HMA to CIR to several of them?
Again, I'd have to go. I wasn't involved in the details of that part of it, but no. I mean, you can get an idea from just looking at the layer coefficients that 4 inches of 4 inches of HMA is sort of equivalent to 6 inches of CIR, that sort of thing. It wasn't huge differences in thicknesses. I mean, again, these cold recycled materials are pretty competent materials. They're not HMA, but they're a whole lot better than aggregate base. So, yeah, Jeff.
Is the assumption in the MEPG that these were bonded, and then or is there no fatigue calculation through the?
They were modeled as though they were asphalt layers because we were putting in as the inputs the dynamic modulus values. So
fatigue performance function is assuming it's a hot mix asphalt.
Yeah, the fatigue relationship probably isn't valid for these. But and so when I say that they failed in rutting, I suppose you could come back and say, well, they may have failed in fatigue if we had used the right fatigue. But to take that a little bit further, I mean, the question came up early on, even in the proposal in the work plan, about do we need to consider fatigue for these materials? And probably for CIR, not so much, because there's often some remaining asphalt underneath the CIR layer, and so these things aren't at the bottom of the asphalt layer. For FDR, maybe arguably more so. The South Africans and the Latin Americans had done some work where they looked at fatigue damage, and it really is a function of stress ratio. And so if you get a stress to strength ratio greater than about 0.6, that's when you start seeing damage accumulating. If you're less than that, it's kind of like shakedown theory. If you're less than that, you're okay. You don't really see much degradation of the material. This is an issue for the South Africans, and they've seen some fatigue problems because they tend to use these materials with very thin surface courses. In U.S. practice, we'd be putting down a couple of inches of hot mix on top of these things, for most of these sections. And so for that kind of a scenario, you don't get the very high stress ratios. And anecdotally, there haven't been any reports of fatigue problems with any of the projects in the U.S. with these materials. Yeah,
Chuck, what kind of emulsion was used here in the CIR, and how long it took in some of the projects to cover it up with the overlay, and how this influenced your results?
It was all over the place. I mean, there are many different kinds of emulsions and different construction sequences, and we've got all that information for the individual projects, and we just, we haven't seen any consistent trend on it. That, again, all of that stuff, eventually it breaks, eventually it starts to cure, and when you come in 6 months later and take a core.
So my question is, after maybe 3-4 months, whatever, the period, are they all the same?
They're not all the same, but if you ask me, could I predict which one's going to be better versus the other? I mean, I think the inherent variability in these recycle processes is swamping any of the causal relationships. At least we're in the process of trying to find the causal relationships, and it's been pretty slow going so far.
Yeah.
So. Yeah, it's on.
Are you recommending mixed design tests at the design phase, or just going to be using models based on gradations and options?
Yeah, no, the whole work is predicated on the assumption that it will be recommending, structural material characteristics for the material based on the assumption that the mixes have been designed and constructed following best practices, and we'll itemize what those are. But yeah, I mean, in all of these mixtures that we're looking at, we're all sort of designed and placed using best practices. These were all projects that Verkin and Kolos were engaged in. And so yeah, if somebody does a really lousy job on the mix design or doesn't get compaction in the field, yeah, then our results that we found here probably aren't going to apply.
Were any of these projects in Iowa where they don't do mixed design?
None were in Iowa, but New York State doesn't do mixed designs either. But what we did with New York State is we got some of their loose material and we did the mixed design tests on the material, so we knew what the tensile strengths were and so on. So, yeah, New York State does a lot of this, and they don't do mixed designs. I don't understand it. So.
Now, this is really interesting because, I mean, that we're doing now the life cycle
Yeah.
assessments.
Yeah.
So this is really complementing what we're doing.
Yeah, yeah, I mean, it's very much along the same lines.
We
Yeah.
need to take you for a dinner so we can get this info.
Were these emulsions the so-called engineered emulsions?
There were some engineered emulsions in there too.
Just add some straight stuff too?
Yeah, and again, I don't think I have the database with me, but we could pull a lot of stuff up. So
that's what I was interested in. To see what the polymer has any impact.
Yeah.
Would you expect the maintenance interval to be the same? I'm worried about your life cycle assessment because you're kind of just treating the front end of this. Not that it's wrong, but if your maintenance cycles are closer together, then your greenhouse gas emissions aren't so favorable.
Yeah, that's a valid point, and I think that the answer to that is unknowable at present. That not enough experience. I mean, some of these projects have been out there for a long enough time, but people haven't gone back and I think really looked at that data carefully. I mean, again, certainly anecdotally. I mean, Iowa's been putting these things in for a long time, and anecdotally, nobody's coming back saying, "Oh yeah, this stuff works okay, but you got to go in 3 years earlier to do an overlay." So there's no evidence of that. So, yeah, question.
Just how vision about the greenhouse gas emissions predicted from different states. Are there any variation comparing different states?
No, and I don't know if our data set was large enough to really do that. I think that this was more in an effort to give us better confidence that the kind of standard numbers we were getting out of the conventional databases. Well, there's two purposes for it. One was to get some confidence that those numbers are correct, and also the verified carbon standard as part of their certification process wanted to see some real data. So we went out and collected some real data for it. But, yes?
So on the process of CIR or CCPR, do you see any degradation of material, and if there is any degradation, like what extent is the degradation of material?
Yeah, I'll tell you the worst case we saw for degradation of material this was early on. We were doing some small test patches, and so we had it was a fire station of all things, and it was a full depth patch, and so we cut out the asphalt, removed the asphalt, placed the foam, the CCPR material, and then it rained for like the next 3 days. And so you still had the lip for the asphalt. And so the hole filled up with water, and it just basically soaked the material for like 3 days. And we could never get it to cure after that. We basically had to take it out and replace it. So, yeah, so things happen. You got to be careful with your weather conditions. You don't want it to rain in those next few days after you place it, because that can really interfere with that can irreversibly interfere with the curing of the material. So.
How about the temperature?
Temperature is important also. I mean, the specifications. If you look at the specifications that a lot of states already have for things like foam stabilized materials, they usually put in a 40 or 45 degree, minimum temperature and rising. Yeah, you certainly don't want the stuff to freeze, and you want it to be warm enough that you actually can get some curing going on. So, Bill.
2 questions. One, what's up with Maryland students and not being able to take our online classes? Kind of a joke, but kind of. And 2, you probably know what I'm talking. The real question is, how do you feel about indirect tensile strength on these materials? I know that, for instance, like Don Christensen looked at going higher and higher in temperature on hot mix with IDT testing, and you start to get just sort of a bearing failure as opposed to a tension failure. Is it still a good number, regardless if you can get a cleft failure or an actual separation?
I mean, I'm not a big fan of doing. Again, the main property we're interested in these materials is the stiffness, not the strength. It's just that traditionally for foam stabilized materials, indirect tension strength at essentially room temperature is what's been used. And again, I just think of it more as an index property that you've got some target you want. It's like flow number. You got some target you hit. Flow number doesn't actually mean anything, but you got a minimum value you got to hit. So yeah.
Okay, so my question was on the base layer which you use as CIR. So you modeled that in NPDG as a stabilized layer, so that it wouldn't be able to talk about suction or or the moisture ingress into it. That is.
Right, yeah.
But do you think there would be any reason to believe there would be problems with suction or, say, with drainage because of using that as a base layer?
Now, when you say base layer, what do you mean base layer? Do you mean like a drainable base layer or a base asphalt layer?
Well, your audience said it would be a base asphalt.
Base asphalt layer, yeah.
But that's a philosophical.
Yeah.
Somewhere in between.
Yeah, it's not. We actually measured the permeability of this material. I don't have a lot of confidence in the numbers, but the permeability of this material actually was sort of within the same ballpark as for the aggregate base. But again, Maryland spec for aggregate base is not very good. They let in way too much fines, and so our permeabilities are pretty low. But in the context of the MEPDG, I have an out on that one because since the MEPDG doesn't model drainage anyway, it's not an issue for the MEPDG. Hopefully that will be a big deficiency that will be corrected at some point in the future.
We're going to take the last
Yeah.
question
Yeah,
from
just
Harold.
a comment actually on the, if you look at the technical guideline document from South Africa, at the sophisticated level, they're doing traction testing.
Mm-hmm, mm-hmm.
That's where the stiffness, they go into that to some extent when they want to do sophisticated analysis.
Yeah. I mean, the South Africans really have a much more sophisticated approach toward this overall. But again, they need to because, I mean, they're putting just chip seals on top of this stuff. And so this is really the main structural element. It's right up there at the surface of the pavement.
Right. I think we have a reception outside if you have more questions.